intelligence and quantum computing, I hand over the word to our host, Dr. Oscar Montiel.
Good morning, everyone. Welcome back to the second day of the seminar. I hope you all are ready for another day of exploration. It's thrilling to see so many engaged participants. Feel the innovative discussion yesterday without examining them education. This talk is short and scarce if 11 a.m. Giving everything the take out. Let me this announce
Shei Tope Ogunji is a graduate of Electrical Electronics Engineering and a researcher in the emerging technology domain. Graduating with honors from Ogun State Institute of Technology in Nigeria, Shei earned multiple awards for academic excellence, including state-level recognition. His passion for emerging technology led him to the coding school in the United States, where he earned a certification in quantum computing. Currently pursuing a master's degree at Instituto Politécnico Nacional in the Center for Research and Development of Digital Technology in Mexico, Shey's research focuses on integrating AI with cybersecurity to enhance digital safety. With a background spanning from industrial automation and maintenance at Procter& Gamble, people management at Hyatt, to founding an AI education nonprofit, Shey brings a special combination of practical corporate work experience and academic expertise. Without further introduction, Shey Owuchi.
Thank you so much for the introduction. Good morning, everyone. It gives me great pleasure to be here today to present this great work for myself and also on behalf of my great supervisors, Dr. Oisis Adam, and my co-director, my co-supervisor, who happen to also be the host of this program, Dr. Oscar Montiel Ross. So my work is going to be on analysis of BB84 quantum key distribution protocol. So I need to give some background to this. Recently, actually on the 16th of this month, there was a research or there was an article that was published that some researchers in Shanghai University, China, they were able to break through the cryptographic structure that was built on RSA. And they were successfully able to do a prime factorization of 50 bits integer. So this showed to us the risk that we're exposed to as a people, the risk we're exposed to as a corporate entity, and the risk the world is exposed to entirely. Because our current systems are built on this stuff, this kind of cryptographic setup, the RSA, the elliptic curve, the Diffie-Hellman. So it therefore calls that we need to do something different for us to be able to have a system that can withstand the power of computing, the quantum computing that we're already at the verge of. And judging by the breakthroughs that are happening in these days, it's just a matter of years. We're going to have sophisticated computing power that are going to be able to break through all this cryptographic setup. I hope that day will not come when everybody want to check his account balance and you see zero because an hacker had break into your account. So I come with one of the solutions to this BB84 protocol. But then before I proceed, there is going to be this table of content, introduction, then I'm going to do the methodology for this work we've done, then the result achieved with conclusions and the future work. For the introduction, there is going to be a foundational work. There is a man called Weissner Stephen. He's an American physicist, American researcher. He actually postulated some uh, theories on how to quantum money. And in 1974, around 1970s, he proposed these ideas. And this idea, two guys, Bennett as the built the work that were described. So the BBA nomenclature was just amalgamation of names of the inventors, Charles Henry Bennett and Gilles Brassard. So they invented it in 1984. That's where we get the 80. BB84, just amalgamation of names. Okay. Foundation. So for the work, it's actually built on some quantum mechanics protocols. Number one, is built BB84. I mean, the protocol is built on the idea that you cannot clone a photon or you cannot clone a qubit. That is one idea that this work is built on. The second idea is the idea of superposition in quantum mechanics. And combining this, we're able to have an algorithm that could do a great work in encrypting our data and giving us a secured security key that will be used for transmission, either through channel, quantum channel, or through classical channel. For us to have a prediction or result at the end of the protocol, the work is built on this particular formula. P correct is actually a function of the cosine of the angle between the senders and the receiver, in this case, Alice and Bob. So the angle, the phase angle between their data sending or between the bases they set up, the theta. So when you take the cosine of it and you subtract it from one, you're going to have one minus cosine. So this will give us the incorrect measurement. But then when you take half of it, it's going to give us the probability of having it correct or not incorrect. Then when you subtract it from one, so you have P correct measurement in P as one minus half of this one minus the cosine of the angle between the bases of Alice and Bob. Okay. Generally, for BB84 protocol, it's built on this basic algorithm. Generally, what we do in BB84 is, number one, there are generation of keys. So this happens at the sender point. In this case, Alice. Alice generates some random keys. She used some state, some quantum state to do the generation. After she had generated that, she sent them to Bob. Bob, on the other end, randomly selects a particular base to do the measurement. And after doing the measurement, there is comparison where there is sifting. In sifting, they will do correlation. The key that Alice used to send the message and the basis that Bob used to do measurements. So they will see correlation. So the places where there is no correlation, they sift it off, they drop the keys, showing that an eavesdropper might be have had access to the channel during transmission. So this protocol helps us to see if there is an eavesdropper that's actually see into this communication line when the qubit or when the message is being transmitted. So there is generation key. The second one, after the generation of the key, there is initialization through a key length circuit. Then there is an iterative procedure that happens for each qubit. So the following are done. Number one, Alice prepare qubits. I said this in random states, 0, 1, plus or minus. Then the next one, Bob does the measurement using Z basis, X basis. Then after that, there is an end. There is base reconciliation. Okay? Thereafter, there is shifting, dropping of keys where there is no perfect completion. Then the is ended. For our work, this one I'm presenting now is built on this pseudocode. Number one, the pseudocode is initialized by BB84 simulator. We actually use an AER Qiskit library. So here we have three parameters as the argument. We have the NI, which is the number of the length of the key. Then we have the J, this is the error rate. Then we have the MK, this is the model, the error that is introduced into the model. For this particular work, 5 types of error models we use, which are the polarizing, amplitude damping, phase damping, generalized amplitude damping, and policy. So the 5 of them were used together at our stage so as to have a very focused and clear clear possibility of how it's going to be performed in a real world scenario. We didn't just limit the setup to one type of the noise model. We use three and five types of noise model to actually see how they will perform over all these noises and things. Okay, after the initialization, so we do this nested loop in the coding. So the first one, we take n. N is the number of noise or the noise model. So initialize and we use say an empty. Okay, as I said before, is the error rate, while the empty is a molded noise. So these are used as the parameters that are used to set up this. Thereafter, after that is done, there is going to be a simulation of PP. Take the another length key, the key length that are used. For this experiment, some range of keys were used from 1,000 and 100 to 5,000. Just see how each key that is. After the simulation are returned, AA signified Alice key, AB signified Bob key. So after this is done, there is comparison. And in the comparison, Bob key done error correction. In this particular work, the error correction model that was cascaded in this, the correction goes Bob, Alice is the sender. So the rep after that, so correction, then there's another layer which is privacy amplification. But that particular work model in this situation, what happens is that in a message has been exposed and he has reached the communication line. So this service amplification ensure that there is a certain level of amplification the pipe at shared generated and have a lot of entropy that will make it very strong such that an intruder will not be able to break through again. And it's on there will be transmission of message between the sender and the receiver. Thereafter, there is going to be a value called R. This is the error rate. This is the key rate. At this key rate, at this point, there is comparison between the initial key length and the final key length to see how many key we have lost in transmission or how many key are lost because of comparison. And after that, set the boundary on how much information classified by using the eventual record. And we have plus here I noise uh and damping noise model which was phase damping noise model and right damping noise model. And the error correction. The error correction, as I said earlier on, gave you the expected right, the reference of energy. The application as I said, this clear magnification and introduction to the key that is the key rate, which is just to compare the final length key rate. The local bond said just certify how much classical information you obtain and the results that you obtain. That rate 0.1. The the level the key rate is 49. The 47 key length of error rate is now sent. Here again, the key length is different. The other one was 2,000, error rate of 5%. The key like, the optimal thing error rate 6. Can actually infer this from the results, which I'm not going to bother you with. I've already explained that in the chat. Then what are the observations that were made from this presentation? Number one, we discovered that there were distinct optimal error. It is saying it's a good thing. Actually, it's good sense of positional fidelity, not a optimization possibility. Narrow, 5,000 across the very narrow. It also to hear the key length, and error, measured error, and the voice system. And this highest variability, highest error, highest error, highest voice just no one size fits optimization. It depends on the use case we have and depends on the problem we want to address. Importance of characterizing the quantum channel is very, very relevant here. Then for future work, actually for this implementation, as I said, I use BB84. BB84 is strictly restricted to base of Z and X, but E91 could be used. Then also in the implementation, I use some part of the finite key effect, but then the full length could as well be used. Okay, thank you everyone for listening. These are some of the references that we use.
Thank you for your presentation.
You,
we have time for some questions. Any questions for the presenter? Oh, I have a question for you. Well, I understand that the BBA84 is a protocol to ensure the secure communication. What are the practical applications of this protocol? Do you have some examples?
Okay, sir. So actually, based on the cryptographic, quantum cryptographic protocol that are being developed now, this is actually one of the most highly performing model. So for all the, even the computing, the quantum computing that is built, the hardware that is built, it's actually built on BB84 protocol because over time it has shown simplicity and as well robustness. Although there are some other models that have been built like E91, as I said in the work, but for now, most of the computers that are built on BB84. It's actually one of the founding protocols for quantum computing security in communication.
Hi, thank you.
Thank you, sir.
Any questions, please?
Thank you very much for the presentation. You mentioned at some points that during the implementation of the protocol, sometimes the key is lost. How does that actually impact the information that is being transmitted?
Okay. So what happened during implementation, after Alice has sent the message, she picked on a random base state, maybe base zero, the quantum state, maybe state 0, 1, or plus or minus. So when the message is sent, she takes note of the base she used for the sending of the message. At the other end, when Bob wants to take the measurement, Bob also chooses a random base to do the measurement. So when that is done, they do eventually come to do comparison. Now, this is the trick here. One principle on which quantum is built is this. When you take a measurement of a particular state, you collapse that state to another, you change the state. So if in the course of transmission, Eve as is dropped on the message and she attempted to take a measurement, actually the idea behind BB84, we don't have a problem that if she is dropped, but all we want to know is that as she is dropped, so we can know, so we don't say you should not come and steal it, but we must be able to know that something has happened. So when Eve takes a measurement, it collapses the state. So by the time Bob is measuring and it is compared with Alice, Alice will say, no, at this point, I use this base to do measurements. Bob will say, no, but this is the result I got. At that point, they will know something has happened and eavesdropper has intercepted. So for that particular measurement, there will be key sifting. They will sift, that means they will throw away that particular key. So at the end of the day, they will align at a point where they have a minimized key length. Of course, it is still okay because afterward, they're still going to do amplification. The essence is we want to get a key that could actually secure our communication. So privacy amplification will still be applied to that final key length that has been arrived at, and then it will not be used for the real message encoding.
Okay. Quantum, I'm not an expert in quantum because I understand that quantum is actually error prone or noise prone, actually, right? And so in the process of transmission of the information, right? What if does noise affects the transmission of information in such a way that Bob or Alice think that Eve has actually dropped the information?
Okay, so noise doesn't affect the state. It's measurement that collapses the state. Actually, in the implementation, you would notice that we actually deliberately introduce noise into the system to simulate the real world activity. So the noise will not collapse the state. It is measurement. And it's actually one of the quantum mechanics principle. It is the measurement that will collapse that state. The noise will just make it maybe inefficient in measuring, but the state changing or collapsing is dependent mainly on measurement, which only the eavesdropper would do. Noise will not cause that.
Please give an applause to the presenter. Well, the next presentation is Type 2 Fuzzy Deep Learning Approach applied to classify Alzheimer's disease by Cesar Torres.
Cesar Alan Torres Quiroz is a PhD candidate at the Division of Graduate Studies at Tecnológico Nacional de México, Tijuana Institute of Technology. He obtained a master's degree in computer science from the same institution. Author of multiple scientific publications in which you can find articles in index journals, book chapters, and proceedings of international conferences. He has been collaborating at Samsung Research Tijuana as a machine learning engineer, working on state-of-the-art artificial intelligence technologies tailored to edge devices. His areas of expertise include computer vision, generative AI, fuzzy logic, edge computing, multimodal learning, and self-hosted services. His current doctoral research focuses on utilizing generative AI technologies to address challenges related to neurodegenerative diseases. I give the word to Cesar Torres.
Hi, good morning. My name is Cesar Torres. I'm from Tijuana Institute of Technology, and I'm going to present my research topic, Type 2 Fuzzy Deep Learning Approach Applied to Classify Alzheimer's Disease. Is it working? Okay, for our agenda, we have the introduction, objectives, background, proposed methodology, and the references. Okay, As we will know, convolutional neural networks are ideally trained on big amounts of data. These are these may contain a wide variety of visual variations, such as low and high contrast, allowing them to generalize in their features and patterns. However, when the images are contaminated with multiple sources of noise, utilizing a pre-processing technique, it's to create a more robust approach can help to improve the results. Fuzzy logic generates nonlinear representations like human-like thinking, assessing levels of uncertainty that can exist in the various sources of information due to the sense in which they are captured. Given the nature of medical imaging, a fuzzy preprocessing technique to suppress noise may improve the image quality or as an appealing alternative. To implement the preprocessing, our objective is to implement a preprocessing pipeline utilizing fuzzy logic to improve the image quality before passing them to a convolutional neural network to perform classification in Alzheimer's disease images from the brain MRIs. Okay, for our background, we got the convolutional neural networks, which are a technique inspired in the human visual cortex and the stimuli from the brain to obtain the patterns. The basic architecture of a convolutional neural network constituted in the convolution layer, activation, pooling, and the fully connected, as well as the output layer. In the case of fuzzy logic, implements nonlinear representations similar to human understanding. This is compared to Boolean logic, which takes into consideration this uncertainty. The concept was introduced in the 70s by Sade due to the limitations of the classical logic. In this case, many authors have tackled the enhancing algorithms utilizing fuzzy logic to pre-process images. In this case, they are mainly based on histogram equalization. Those go from the clustering of the data of the histogram to creating to processing the grade levels from this. Okay, so for the proposed methodology, we would like to implement a image enhancement inspired in traditional control enhancement techniques, where the brightness levels are adjusted for the visibility. In this case, we propose a type 1 and type 2 system approach to improve the image quality before passing them to the convolutional neural networks for the classification task. For the type 1 system, we utilize two values, the mean and the standard deviation. These values range from extremely dark to extremely bright. So we have 8 divisions for them, and they are calculated from these values. They go from 0 to 305, which is basically roughly the level of the image, where 0 is pitch dark. In the case for the type 2, we also implement the foot of uncertainty, where it ranges from 0.2 to 1. This parameter is, this is presented in these equations in the universe of discords, is the standard deviation of the means of the images. Here is the knowledge base utilized for the fuzzy model. In this case, we utilize AND operators for our system, and we implement a differentiation by centroid to obtain the images. Here is a visual representation of the functions utilized. And to test the images, we proposed a real simple convolutional neural network that consists of 5 convolution layers, the dropout to eliminate overfitting, and two fully connected layers before going to the output. It's a pretty simple model. Okay, for our experimentation, we first tested on Alzheimer MRI dataset version 2 from Kaggle. It contained 4 different classes, which go from mild demented, moderate, non-demented, and very mild demented. The dataset contains 4,000 images and in a really small resolution, 179 to 208 pixels. Here is a small example of the images. In this case, we can see the classical image the grayscale, the histogram equalize, and the fuzzy type 1 and fuzzy type 2. There are some visual variations on each image in the contrast. The models were trained for we did 30 separate experiments. They were trained for 20 epochs using cross-entropy laws and the Adam optimizer from the experimentation. And here are the results of the model. In this case, we can observe that when we apply the constraint enhancement, with the interval type 2 fuzzy logic, with a field of uncertainty of 0.6, we got about 99% of accuracy with our best model. In this case, we perform a statistical test to conclude the existence of significant evidence. It was a rate tail test, and we tested for the utilization of a processing technique that offers a significant boost in precision. And well, here are the results. We also did a second experimentation with a dataset that we got access to. It's a dataset by request from Washington University. It's called OASIS 1. There are 3 variations of this dataset. It contains the same 4 classes, but it's a more robust dataset with about 85,000 images. In this case, we know that they are tested from 416 subjects from 343 sessions of MRI sessions. So this is real data with a real split. Here are some of the examples of the images obtained. These ones are a little bit more rough, and they need a little bit more treatment before being processed. And well, we utilize the same model with the same parameters to test the images for the classification. And in this case, due to the large amount of data, we got a accuracy of 100%. We did a 80-20% split to perform the. And in this case, in Nolavi, we can see the standard deviation, which goes from almost 14% to 17%. Okay, for our discussion, when we performed the experimentation with the first dataset, we got a nearly 4% of accuracy improvement, which are roughly 60 images or 60 cases compared to the first system. In this case, we got a 99% of accuracy, which is really a real good result due to the nature of the images. And the field of uncertainty of 0.6 be the 0.2 and 0.4, suggesting that this is the optimal setting for this case. However, regarding the OASIS data, we trained the trainer demonstrated range of accuracy ranging from 71 to 81%. And not totally some of the models achieve a perfect accuracy. However, it was a significant variation in the minimum accuracy. So from 25 to 62% from those models. And well, with the augmented data set, we got that the 0.6 was a setting for this case. However, the application of the type 1 and type 2 in some cases was not optimal, than the more optimal than traditional equalization. In this scenario, we are sure that the application of image preprocessing are not only good for the model, but also for human interpretation, because being medical data, it needs to be validated by an expert to perform an assessment. So it also allows the medical personnel to confirm their findings over those MRIs, and consequently making experts more precise and well-informed in their diagnosis. And for future implementations, we would like to experiment with more intervals. In this case, because we were limited by the time of preprocessing right now, because there are a lot of images, and we will also like to perform parameter optimizations through a methodistic algorithm. In addition, we would like to expand our pool of datasets, because right now we only tested on over 2. In this case, we have also access for OASIS 2 and OASIS 3, which are more modern images, but tailored to different ranges of ages. In this case, OASIS 2 is for 50 to 80 years, and OASIS 3, I think it's for younger people. And we will also like to apply the approach in utilizing more monitorings for classification, like the visual transformers that in the common literature have been demonstrated to have an impressive general capabilities. And well, here are some of the references. Any questions?
We have time for some questions.
Hi, thank you for your exposition. How large or some of the sample did you use for the experiment? That's the first one. The second one is what is the stochastic method did you choose for the sample? And the third is what age range are you patients subjects for the sample? The age, the large, and how you chose the sample.
Okay, for the sample, we had, well, for the first data set, it was a data set that we got from Kaggle. It was an augmented data set based on well, it was actually Alzheimer's disease version 1. So we don't have a range for that. Well, in this case, we did an 80-20 split. Just we base ourselves into the distribution of the classes because there is a discrepancy. Not all the classes have the same amount of data. So we just base or splitting that. And well, for the first data set, we are not pretty sure about the range of ages. Yeah, we use the same split 80-20 for both of them to test them. And what was your other question? Okay.
Thank you so much for your presentation. It's quite encouraging. I have a question concerning the accuracy you reported. One of your methods had, I think, 100% accuracy. And then in your conclusion, you also mentioned that probably in the future, you work more on your hyperparameters and some other methods for optimization. My first question is, why do you need to optimize when you already have 100% accuracy? So the second question is about the metrics. For your classification task, you only reported the accuracy of both models. So I'm curious about other metrics that can be used to evaluate the performance of your model. As it is, I assume that accuracy is not sufficient to tell how robust or how good a model is. So those are my questions.
Well, as you saw, we had with the model that got 100%, we got a lot of standard deviation. So we would like to reduce that to make the models more concise because we performed 30 experiments right now. So that's what we would like to reduce, that variance between models. And basically that. And for the other metrics, well, we were considering another type of scores like F1 score. But by the time, due to time constraints, we only tested for accuracy and did the C test right now. So we're open to perform more metrics. In this case, we were not testing only for model accuracy, but more simple model, not something more intricate like a BGG or eResnet. Yeah, we have, well, the raw images, they were roughly like we compare ourselves with the equalized images. We perform a traditional histogram equalization. That is a well-known technique for MRI data. And that's what we use as a basis.
Okay, thank you. Please give an applause for the presenter. Next presentation is Quantum Deep Learning for Bone Fracture Classification, Enhancing the Quality of Medical Imaging by Daniel Alejandro Lopez.
Daniel Alejandro López Montiel graduated with honors in biomedical engineering from Instituto Tecnológico de México, Instituto Tecnológico de Tijuana in 2021. In 2022, he pursued a master's degree in digital systems at the Center for Research and Development of Digital Technology, Instituto Politécnico Nacional, where he graduated with honors in August 2024. His thesis centered on developing hybrid classical quantum methods for computer-aided diagnosis of spine fractures in medical images. Currently, he is continuing his research as a PhD student in digital systems at the Center for Research and Development of Digital Technology, Instituto Politécnico Nacional, with a focus on machine learning, deep learning, high-performance computing, quantum computing, and quantum machine learning, particularly applied to medical image diagnosis. I hand over the word to Daniel.
Thank you very much for the introduction. Hi, good morning, everyone. Thank you all for being here. Today, I'll be presenting the work titled Quantum Deep Learning for Bone Fracture Classification, Enhancing the Quality of Medical Imaging. So we'll briefly take a look at the background of the problem that we're working with, some of the things that have been done and why did we choose this methodology, and our approach for this particular problem, and some of the results that we got, and finally the conclusions. So the problem that we're working with in this case is osteoporosis. Osteoporosis related spine lesions, in particular, one of them is bone fractures. They severely hinder quality of life, and they are mostly defined by having low bone mass density. As you can see here, males and females present a difference, not only because they're different, but also as we age. And other conditions such as puberty, menopause, and in the case for women, pregnancy can change this aspect, which is important to consider. In here on the right, we can see the difference between healthy bone tissue and unhealthy bone tissue. Here we can see that it becomes hollow and fragile, which can lead to spine lesions, such as spine fractures. So why did we choose quantum deep learning and deep learning in particular, and then from there, build onto it to get to quantum deep learning? Well, initially, deep learning has demonstrated good results in aiding spine fracture diagnosis. This is the aim for these kinds of models, enhance diagnosis, medical experts, diagnosis and assessments by highlighting the regions of interest in these medical images. And as you can see here, it's been demonstrated by the state of the art that this can be achieved. And that why do we focus so much on quantum machine learning? Just to go over some of the key points that one of the most prolific authors for quantum machine learning brings up is that although there's differences between the two fields, we can bridge the gap by not only trying to get the potential improvements from quantum machine learning, but also try to achieve that shift in paradigm, changing from classical computing to quantum computing. So now let's head over to the methodology. This particular problem is interesting because we are focusing on a very recent problem that was just published. If you know the Kaggle website, this website publishes challenges and data sets that focus towards data science. So in this case, just I believe in 2 months ago, it was published this competition, which was published by the Radiological Society of North America, which teamed up with the American Society of Neuroradiology. And they defined a competition to explore detection of degenerative spine conditions using MR images. Essentially, the challenge is trying to focus on 5 lumbar spine degenerative conditions across different intervertebral disc levels. What we are trying to achieve here is to predict a probability for each of the images that we have here, so that we know so that we can predict what spine degenerative condition this image is presenting. So what did we do here? There are different ways of approaching this problem, as it was just recently brought up. This is the data distribution that we have here. As you can see here, there are 3 different spine conditions that we have to consider: canal distribution, subarticular distribution, and foraminal distribution. These are all different kinds of problems that we can present in the spine caused by osteoporosis. And as you can see here, they are all divided by 3 different degenerative conditions, which are normal or mild, which is the predominant class, the moderate spine degenerative condition, and in some cases even severe. These diseases, these conditions are all throughout the 5 lumbar spine vertebrae, as well as the first sacrum vertebrae. Essentially, this problem is trying to put researchers to work. It is trying to emulate what we would get in the real world. The data has been used to train the model, and now we're trying to assess if it is able to perform on real world data. So how do we prepare this data? In this case, we have these data samples. These are 3 different perspectives from the MR images that we have here. And here, the little red dots highlight some of the key points from the image. Each one of these red dots is focusing on each of the intervertebral disc levels that we are working on, from L1 to L5. And what we're trying to achieve here is take that information, which is in this case very small, so that the model is able to train effectively. So we take those regions and we crop them and generate a sample for each of these intervertebral disc levels. And each of them is labeled. As you can see here, we have 3 different perspectives view: the sagittal T1 view, the axial T2 view, and the sagittal T2 stair view. And all of them have been labeled with their corresponding spine degenerative condition. As you can see here, they're relatively small images when compared to the big MR image. What we're trying to do is use these samples to feed the model and train it so that it can effectively distinguish not only between these levels, but also the degenerative condition that they present. The model that we selected in this case is a relatively simple model. It's a ResNet 18 medium-sized model that is residual and is able to achieve good results, but also avoid overfitting, right? And it's relatively efficient when compared to its counterparts. And particularly, we took this approach, which could be called a multi-view deep learning model proposal, which all has already been established by the state of the art. What we have here is we have 3 different perspectives, as I just showed you, right? We have the sagittal T1 and T2 view and the axial view. So we're going to use the ResNet 18 architecture 3 times here. And each of the models is going to be focusing on a different perspective. Then once they are used, they can use their probabilities, their performance on each of these perspectives in order to give a classification and a prediction for the rest of the samples that we are trying to classify. And in regards to the quantum machine learning model, we first define a quantum circuit. In this case, it is a circuit, 4-qubit circuit. And first, we are using this angle embedding layer, which what does is just encode the data from the classical state to the quantum state. Then we have defined 2 sets of quantum gates. These 2 are similar to classical convolutional layers, in which they use entanglement to extract features from the input dimensions that we have, and then a quantum pooling layer that averages out some of these features by using Hadamard gates. And finally, when we measure back these values, these features that we've extracted back from the quantum state that they were in, to back to the classical state so they can be further processed. So our model looks very similar to what we had in the beginning. We are just implementing these quantum layers at the end of each of our models, so that we end up with 3 unimodal hybrid quantum models. The metrics we used in this case are relatively straightforward for the training and validation sets. We are going to be using the classification metrics of precision, recall, accuracy, and F1 score. However, for the test set, because we do not have labels, we'll be experimenting on the results, and you'll see in just a few slides. So we're going to be the accuracy. One thing to note here is that the number of epochs is relatively small because we implemented the value of patience. So if the model does not improve over time, I believe we established it as at 5 epochs. It just stops there and saves the best weights, the best version of the model. The same case is for the rest of the metrics. The model does improve for the case of precision, but for the other 2, it stays relatively the same. For the axial T2 view, the model does underperform. In this case, we get around 50%. This is due to the fact that the axial T2 view is a transversal cut. So there's very little information for each of the intervertebral disc levels, as we saw in the beginning with that perspective of view. And when it comes to the other metrics, with the exception of precision, we get the same behavior. And finally, we get the sagittal T2 perspective. In this case, we can see that the model is now able to get more information, so it is able to better generalize the model, the problem, sorry. And we can see the same case for the rest of the classification metrics. So this is the interesting part. Because we don't have the test set labeled, we're going to take a look at what the model is focusing at the last layers, meaning that let's say if we have a medical expert on site, we could see if they are, focusing on the same things. In this case, we plotted the heat map, meaning that the regions, the heat regions that we can see here in this image, are the ones that the model is focusing on. And when we overlay them, we can see that most of the time the model is focusing on spine regions, as you can see here from the original image, the GradCam heat map, and the overlay. Although it is a bit difficult to see, and I believe there's might be some issues now, looking at it from afar, but essentially it is, focusing on the particular spine regions. Another way of looking at our results when we don't have labels for our test set is to look at the probabilities. Essentially, the model gives us a probability that this sample belongs to a particular class. And what we see here is that it shows a trend where most samples apparently are not from the severe class. And this is to be expected because of the distribution of the original data. As you see, there are very few severe cases in the original data set. So that's why the model is saying, okay, I believe there are not many severe cases. And for the case for the other two, which in this case is the majority class, and this is the other one, the model is a bit unsure. There is even a big gap here between 0.4 and 0.8 probability. But mostly, the model is leading towards the middle right here for the moderate probabilities, meaning that the classical model is most of the time predicting that the samples are either moderate or normal and mild. What about the hybrid quantum model? Well, we see something interesting here. The hybrid quantum model is able to improve performance in sagittal T1 view for the accuracy results, as well as the training recall, the F1 score recall and precision. And we can see the same thing for the axial T2 view. Actually, here there is a big jump, about 10%, I believe, in performance. And this goes to show that the quantum layer has been correctly implemented, and it is able to extract features that the classical version was not able to. Even here in the precision, we can see that it was a jump from 60% all the way up to 77%. And the other metrics are relatively close to what we saw in the beginning for accuracy. And for the sagittal T2 view, it is still a leap of improvement. However, it is not as big as the other one, right? We are getting around 85% here, and the other ones are 87, 85, closer to what the classical model got, still an improvement. And when we take a look at the results of the heat map, the model is focusing on more specific regions. Sometimes it might make mistakes, as you could see here. It could be interpreted as one, or maybe it could be that the spine lesion is all the way down here to the L5 section or S1 section. As we do not have labels, we can at this point. But you can see here, this is an interesting way of looking at the results that we get here. And here we see the biggest difference. The model is being more careful with the predictions that it's making. As you can see here, it's more towards the middle, those predictions, those probabilities. So it is trying to tell us that it is unsure if the classes are either moderate or normal and mild, but it is still somewhat certain that there are not many severe samples, as it is the minority class for the data set. So when we compare the results here in this table, we can see that the hybrid quantum model was actually able to outperform in each of the classes, each of the perspective views, and also each of the metrics. So what can we gather from this? Well, we proposed a ResNet 18 multi-view model that demonstrates that it is able to solve these issues for different perspectives, attaining 82% and 85% of accuracy. And the proposed quantum circuit in this case is able to improve performance on around 5, 10%, and 3% in their respective views. And as a result, the hybrid quantum model that we propose here is also able to outperform its counterpart, its classical counterpart, by this much. And at the end, we can see that there are definitely many ways of evaluating test sets that are not labeled. In this case, we opted for gradient analysis to see a comparison more similar to what we would get if we were working together with a medical expert. And we can see here that it is an interesting way of looking at things, and it might enable further tuning and performance evaluation. And we also worked with the probability distribution, which is also interesting to look at. Future work We could explore different model architectures, such as different classification models, residual models that are larger, or other kinds of models. We could also experiment with different approaches that consider more of the features that were provided. As you saw, this is just one way of approaching the problem. There are many ways as we have a lot of data, and we could explore other kinds of quantum circuits. That'll be all for me. Thank you very much for your attention.
We ran out of time, so feel free to reach the presenter. You have
I'm so sorry.
for him. Thank you for your presentation. The next presentation is Vision Transformers for the segmentation of pixel patterns associated to pathology in diabetic retinopathy, a literature review and clinical relevance in eye fundus images by Jenner Jose Avilés Rodriguez.
Kenneth Aviles initially trained and practiced as a medical doctor before advancing his education with a master's degree and a doctorate in science focusing on data analysis of scenarios within the health illness continuum, both for individual patients and broader populations. Dr. Aviles is also a member of Mexico's National System of Researchers and the National Young Academy of Mexico. I give the floor to Kenneth Aviles.
Can you guys hear me? Yeah. So the work that I'm going to talk about is the product of a team that is part of the telematics research group in UABC, in Senada, Fiat, and a collaboration between School of Health Sciences and Fiat. We are trying to develop a research line that helps us start what we call computational medicine, which is the application or the application of algorithms, mathematical models, or algorithmic models to approach the health disease continuum. I'd like to say that I am a physician by training, but I like to say that I do medicine through algorithms. To give this context, to put all of us in context, that retinopathy is one of the main problem for diabetic patients if diabetes is not well controlled. Usually, it is first detected by a simple direct eye fundus evaluation. And what we do when we perform an eye fundus evaluation is we look for the fundus of the eye ball, and we try to find the three main anatomical regions: the optic nerve, the blood vessels, and the macula. This is usually performed through digital images, and physicians usually look for indicators of pathology, specifically talking about diabetic retinopathy. The problem here is that in Mexico, there are 3.6 eye health specialists per 100,000 people. So it is not enough. It will not be enough soon. So most of the patients that go to an ophthalmologist and have problems with diabetic retinopathy will usually be patients that had to be diagnosed probably 5 to 6 years before that first consultation. And most of the time, ophthalmologists cannot offer something to slow down the progression of the disease. Usually, they just have to do treatments that cannot save the sight of the patients. Usually this is done or performed assigning severity levels. Also, the interpretation is performed by eye health specialists, as I was telling you, and there is a level of complexity in interpreting fundus images. Also, there's a need for accurate and automated methods for large-scale screening, given the limited amount of specialists available, as I was telling you. If we were able to generate an automatization of this process and be able to find those patients in high risk of developing sight loss and send those patients before to the specialist, then we'd be doing something good to our population. But this cannot be done through ophthalmologists since there's so few, at least in Mexico. The same trend is for all Latin America. So thinking of this, there are some advancements in AI for medical diagnosis. We have seen some examples now, and I think we can all agree that the medical field is a very attractive field, specifically talking about medical images for implementing computational approaches to this. And the role of CNNs, or convolutional neural networks, essential for the automation of diagnosis, specifically in the medical field. However, there are some struggles to capture long-range dependencies, and this is important to put in to give a context that makes sense for the clinical world when a CNN gives an output. The introduction of transformers was in 2017, specifically for NLP, and these tools seem to be attractive, specifically for this task, keeping long-range dependencies. In 2020, the vision transformers were introduced, and this started to generate a lot of interest, specifically for medical images. There are a few studies on visual transformers, less studies on visual transformers applied to medical images. And when we talk about only evaluating eye fundoscopy, there's even less. So we wanted to know exactly what was the state of the art of the use of visual transformers for eye fundoscopy when diagnosing diabetic retinopathy. So that's why we decided to perform this study. Review recent literature on visual transformers and diabetic retinopathy classification, and evaluate relevant metrics of what has been published so far. We performed a systematic review. We used a PRISMA methodology. This methodology is applied or is used in healthcare research, and is also very friendly when using technology. We use PubMed, IEEE, Explore, Scopus, and Google Scope. Basically, we focused on visual transformers, eye fundoscopy, diabetic retinopathy, and terms alike. We started with 558 papers and ended up selecting 20 of them. So I'm gonna have to go faster. This is the taxonomy of the concepts that we found, and I think this is part of the most important things that I want to show to you. It was very interesting to find that, at least up until now, visual transformers only per se are not the most used or not the most experimented with when it comes to diabetic retinopathy, but transformers models, combining transformers and convolutional neural networks, came out to be very, allow me to say, popular in our subset of papers. This was something that caught our attention. There's some examples of only visual transformers. We call them non-hybrid models. And most of them are using multi-class classification. And this was something that we found very important. Usually, diabetic retinopathy was attacked as a binary problem. But in the clinical world, that doesn't make sense. Diabetic retinopathy is a multi-class problem, classification problem, if it's going to make sense when we take it to the hospital, when we take the algorithm to the hospital. And these hybrid models and non-hybrid models, most of them are focusing on segmenting things that usually the human is going to segment, or the ophthalmologist is going to segment. So the output of these algorithms will most likely make sense when it goes to the hospital, which is something very interesting. One example, just to show hybrid model. This is the part of the visual transformer, and then the VDG16, and then the output of the two was fed to a classificator, a machine learning classificator. And this is an example of a non-hybrid approach when a visual transformer was only a visual transformer was used. Patch embedding was performed, then positional encoding, then it went into the encoder, the decoder, and the classification had provided a multi-class classification, which again, this is very important. And we were very pleased to find that most of the papers now are thinking of this as a multi-class classification problem, which is what makes sense in the clinical world. If this is where we would like to spend the rest of the time. We have 5 points for the discussion that we'd like to share with you. Computational demands of transformers. Yes, this is attractive, but the computational demands of applying this or implementing this are could limit the translation into the clinical world. It is up until now, it's challenging to convince an informatics department to invest in computational power. So this is an area of opportunity, and also the idea of optimization. And another point that is very important that we think it's very important, the role of hybrid models in diabetic retinopathy classification. It seems to be that the path forward is hybrid models, at least now, because this will lower most likely lower computational cost, and also allow us to provide classifications that make sense in the clinical world. So, importance of pre-processing. Most of the papers that we found used class as a pre-processing technique. Also noise filters, tools that come from digital image processing. We could say typical tools, but the power of these tools was shown in the output of the algorithm. The better pre-processed image, the better result that usually was reported. And lesion detection as a key of diagnostic metric. We could use all the metrics that are used in the literature, and that is important, but we think that we also have to start thinking about metrics that tell us about lesion detection, hemorrhages, microhemorrhages, cottonwood bodies, and amount of cottonwood bodies that this algorithm can detect, because in the clinical world, this is what the ophthalmologist is looking for. The ophthalmologist might not be too excited about F1 score, and it is important. It is very much important, but they won't understand it. But if we talk to them about hemorrhages, microhemorrhages, they will stay that. They won't turn it off and then go see patients. They will keep it and take it with it while they see patients. And also the need for explainable AI in clinical settings. I'm saying this with a lot of caution, because I want to say that explainable AI should be defined by the domain of the data, where the domain the data is coming from. So if we talk about the clinical data, clinical world, explainable AI is those metrics, those indicators, those outputs that can be easily understood by the healthcare task force. Probably not automatically understood, but with a light training, easily understood. And those explainable AI metrics can be part of a healthcare system or information system without too much effort or without too much training to the clinical setting or clinical team. So 4 points for the conclusion. There is obviously a potential for vision for diabetic retinopathy diagnosis, at least within the subset of articles that we read and analyzed, but there are some challenges, specifically when it comes to the clinical adoption of these tools.
And at the end of the day, if we are going to perform or if we're going to pursue computational medicine, what we produce should end up in the hospital or it should end up in a doctor's office, and it should end up affecting people's lives, just as a stethoscope affects people's lives, or just as a echocardiogram affects people's lives. An algorithm should also affect people's lives. And how do we do that? Probably we do it by adding metrics that make sense in explainable AI in the clinical world and other things. This point three, I think it's very important and it's shared by other discipline areas. The need for lightweight and interpretable models. I'm going to just talk about lightweight. This trend, we can see it in the industry, this mega trend of how can we make it lightweight? This is a very powerful model, but let's make it lightweight. How can we optimize it? Same thing for the medical world. It is very hard in a hospital to put a whole lot of money in computers and not give them metrics that impact people. It's hard. Future directions for explainable AI. I think this I've already talked about enough about explainable AI. We should define explainable AI by the domain the data is coming from. At least this is what we found within these 20 articles. And towards more complex tools, always welcomed as long as we can make them, we can make sense of them when they go to the hospital. No? Thank you very much for your time, and I just ran out.
Thank you for your presentation. We have time for some questions.
Thank you. Thank you for your presentation. Very interesting. I have a question about what other future wars like are you focused like in efficient deep learning, efficient vision transformer, for example? MIT is working in this kind of issues for reduce the complexity, the opposite of building on parameters for ChatGPT, not dependent of the cloud-based infrastructure. So are you considering doing similar research like these ones in order to focus in these kind of issues right now for clinical applications?
That's a very good question. We decided to perform this work in order for us to have an understanding of the environment, of the actual environment. What you say, I agree 100% with what you say. I cannot say that we will focus only on that because computational medicine is an interdisciplinary field. So what I can say is that we are going to pursue alliances and works that with people who are experts in that particular area of optimization. Because if we focus only on that, we might lose focus of impacting our patients. Sometimes I speak as a physician. I'm sorry, but at the end of the day, people have to be impacted. People's lives have to be saved or improved. And for that, I don't see any other way of moving forward but interdisciplinary work. What I can say is, yes, we will look for alliances and colleagues that can help us attack this particular part of lightweight models. Thank you.
Thank you so much, Doctor, for your presentation. I'm kind of excited to see someone coming from the medical line and then coming straight into data science, data analysis, and computational medicine. So my question will be kind of in line with Miguel's question. You spoke about the potentials of transformers, but at the same time, you talked about like the disadvantage, which has to do with the computational demand. So, but you spoke so well about transformers, saying that transformers perform better than convolutional neural network, especially in the area of the disadvantage you highlighted in one of your slides. So My question would be taking both sides, trying to strike a balance or trying to come to a trade-off. Would you advise that we kind of like switch back to using convolutional neural network and then kind of still chill a bit about the use of vision transformers? That would be my first question. The second is about the clinical adoption of these tools in real life in the health system or in the clinic. So coming from a medical background, do you think, no, coming from both background now, both the medical and the data science, do you think that explainable AI is sufficient to bridge the gap between the medical and the technological experts so that there will be adoption of more technological tools in clinical use? That's my question.
You've asked two questions that will take a lot of time to answer, but the first question, my RAM memory is short, so could you remind me of your first question, please? just the concept. Oh yeah. Thanks for the question because I didn't have time to do this, but this will allow me to do this. I don't think the way forward is going backwards in technological tools. I think it's different. It's a switch in how we see the problem, and how we see the problem for improvement. To improve how we see the problem, we should go to the domain where the data is coming from. Physicians look. You can look at a physician as a classificator. That's what when it comes to diagnosing diseases. So if a physician, what it does, it takes a lot of information, but it doesn't take it in bulk. It subsets the information, and this is telling me about this. This is a microhemorrhage. This is a huge hemorrhage. This patient is diabetic, or it has been diabetic for the last 10 years and is not well under control. And all these information, all these data points are integrated and then fed into the classificator, which is the physician, and then the physician gives an informed diagnosis. I think that's the way forward. Just using a bio-inspired approach. We can use transformers. Yes, I think we should keep looking into how best to use them because they are very good at long-range dependencies, and that's something that CNNs tend to not be as good. But I don't think transformers are the answer or the answer that is going to make the others obsolete. I don't think that is at least in the clinical world. We have to be looking into all the tools and see how best to integrate them. So if a transformer is going to give me a data point or a subset of data that makes sense to give it to a classificator, be a human being or algorithm or an AI algorithm, then that is the way forward. That's my first approach to your question. And the second question, oh yes, we could be, yes. Again, I think that just two questions, just two ideas. AI is not coming to get rid of physicians or the healthcare task force. That is for sure. But physicians or people who in the healthcare professions who learn how to use these tools will get rid of the other one. So I tell my colleagues in the clinical world, don't be afraid of algorithms. Be afraid of your ignorance because someone else is going to come and get rid of you, man. Don't be afraid of the AI algorithm. But that raises a very important question. How are we training the next generation of healthcare workers? I think that is the question to your the answer to your second question. The way we train the next generation and the way we kind of give an up-to-date an updated training to the ones that are already in the task force, healthcare task force. We need to rethink how we train healthcare people, and we need to do it in this approach of hybrid professions. healthcare professionals should know way more about computers. This is not because I did my doctoral degree in computers. No, no, no. I'm not biased that way. It's just computers are everywhere. They're part of our lives. They're integrated. Therefore, every profession who heavily uses informatics and computers should be should be trained in a minimum amount of knowledge in computers, and that is true for the healthcare. How we do it, I don't know. That's another talk. That's another talk.
Thank you for your presentation.
Thank you.
Please give an applause.
María de Los Ángeles Cosío León is a doctor in science from the Universidad Autónoma de Baja California. Currently a member of the National System of Researchers Level 1 by CONACYT. She holds a certification in artificial intelligence from Huawei and has completed a diploma in applied artificial intelligence at the Potosino Institute of Scientific and Technological Research, as well as a course at the Huawei International Training Center in Hangzhou, China, focused on large language models. Since 2018, she has served as a research professor at the Universidad Politécnica de Pachuca. Her research focuses on the study and design of algorithms for data preparation and analysis, as well as data ecosystem traceability. Additionally, she works on optimization techniques based on statistical methods and reinforcement learning applied to the quantification of components in crude oil. Without further introduction, María de Los Ángeles Cosío.
Uh, Thank you for your introduction and thank you for being here. And I want to say another thank you to Henner and the lady making us some questions, some interesting questions. I don't know his name because we are um, we are working for 1 year almost, and most of these questions uh, has been done by some clinician. So we try to show some thoughts about these issues. Let me check this here. Oh, okay. We are working to help to build a library, a digital library with image and several types of paraclinical studies. We are working in the same project of Dr. Oscar Montiel, and we are trying to gather image. It's hard to gather this kind of data. Several times we people close doors to acquire to have access to their databases. And now we are working with INS Bienestar from Hidalgo to gather this information. However, it's hard to talk about the AI. People don't believe that this can be true in clinical spaces. So more when we are working with this kind of vision of AI, responsible AI imply human rights, imply promote equity, imply generate mechanisms that make transparent, safe, and reliable process to manage information. some of the key principles of this kind of AI. Talk about ethics, transparency, and in fact, we are working at this time about the privacy and security are the most relevant points that we are working. Another element is data ecosystems. Data ecosystems are a space where elements are hardware, person, and data interact with. And we are working to build this kind of space. Another element is data traceability. To work with this kind of data in medicine, we need to provide this kind of elements. Where is the source of information? What kind of modification we do in this kind of data? Who use this kind of data? Why they use this kind of data? This question must be answered to move some barriers to use this information, like rules in Mexico and several countries. Another kind of concept here is the ethics controls inside of the hospitals, and we need to add this kind of elements. Key aspect of data traceability is to know about the source of data, transformations, data movement, access and use of this information, and compliance and auditing. These elements are key to have to use the hospital data by our process. Another element that we are using in this is data as a service. The concept here is that we provide data, but with all the safe elements, and we can connect different source data warehouse, operational data, data lake, and external data that finally users that can be mobile application, that can be external user or web application can provide services or can provide solution or can use models to show some solution to specific problems, like all of you are show along these 2 days. We are working all in backstage about data. A common structure that many companies has is this kind of structure where several sources of data connect to a process ETL that in this stage data is transformed and is information is gathered from this source and finally is storage in the data warehouse of companies. Here in the data warehouse, we can find metadata, summary data, or raw data, like you use once you can do some analysis or make some process of data meaning or only generate reports. This kind of structure, as you can see, don't provide elements that can do traceability or can protect privacy. And these kind of elements we saw to propose the digital library. This is a classical system to use image in a clinical space. Here, several clients can use of this information through an authentication service. Once the user is authenticated, they use clinical packs image as finally there are in back some processes to gather information, and the service of this kind of system is to show solutions or use models or to show some cases. This is the intention of this. Facts you can find in the literature without AI. It's very common. But once AI is added to the system, this kind of system can provide some answers to the clinician, or this kind of system have the capacity to make a diagnosis. Here, for this case, the digital library is an ecosystem that we are building with information of Mexican people only. This is the intention. So so the problem that we try to resolve is focus on the ecosystem that do not have mechanisms to certify ethical, transparent, and secure management of clinical data. Once we present this approach in the hospital, docs were open, but not before. Before was hard to talk with these people about the use their data. And when we start to talk about this condition, people was more agree to give access to this data. So this lack of negative effects affects the traceability of source of data, the certification of process, and the protection of personal data and sensitive data, the most relevant things. Here, Henry was talking about that training process in health institutions. This was another element interesting for these people when we talk about the training, the medical personnel, how you will do this, and we share some ideas, and we start to work with them in this part about the training processes for clinicians. One of the answers that we have in this case is blockchain technology about to try to make transparent actions in this platform. We try to follow the role to anonymization of DICON objects. Here, a classical structure. We don't want to find more money, only to trace how the process of anonymization is working. And why? Because institutions like INAI here in Mexico, we need to prove that we are doing correctly this kind of process of protecting people information. Here exists a bridge between this word, classic, protecting information, like asymmetric keys, and talking about the quantum computing. We need safe space because here it's necessary in case that the people want to revoke donation. We need to have the capacity to do it, and if we have no safe space, people and health institutions maybe don't want to allow to training or models. So here we saw a bridge between this kind of technologies that do work widely to protect the information of people that can provide medical information. In this case, that's why we are using blockchain. This is the reason. This is an example. We are proposing to use blockchain in the when the data get inside of the ecosystem, and we propose to use blockchain, another chain, when people use this kind of information that was storage in the ecosystem that we are building. And this is a basic structure, the initial structure that we were working to protect data. Here, some of the technologies that we are using to develop Postgres. This database is used to storage people that is using and that people that is giving us a image. This is Go is using to build the backend of the space. Red is the front end. In this case, in HTML is the other software. And MongoDB we are using to storage image, diagnosis, and all elements related to paraclinical studies. And finally, Definity we are using to develop blockchain technology. In this case, we need to provide a protocol, and finally, if this company think that our project is interesting for them, they support us with the technology. In this case, we will do it. We will work with them the next year. That's it. This is our first version of this technology. The Dr. Tanya is part of our team, and in this case, the student the students were having a course about this kind of images and how to detect some problems in the image. Here, some students from Terapia Física of the university working with this information. This was our first version or first approach to this solution. What we can do? We can do a learning data ecosystem by and for health professionals, humans and AI model for the hospital environment. This is our intention. We not only want to training models as you do, we try to also to train in health professionals. When we talk with people from hospitals, they are really interested in this part. That's why I say thank you, Henner and take you to the lady, I don't know his name, again, because these questions are open with them. When I was when I was talking with the doctor, they told me, okay, go ahead. We will try to understand AI, and we will try to do enough information. This kind of environment are open new opportunities to research, to move that some solution to the clinician, like for example, some specialists of the hospital will help to make diagnostics on image. So it's hard for them to type in all the time. So only 3 people will be working with this tasks. So they ask why don't record or diagnostics and move this to the text and save the information. This is a work that we have. Now we are working with some AI like Notion to provide, oh my time, to provide, I lost the time, to provide some, to provide some solution to the some diagnostics and to check with the solution that medical is giving us. In this case, Medico Tania Aparicio is working hard with 10 students making diagnostics. Dr. Felipe de Jesus Zenobio, this man has helped to become in reality, to become real that this kind of work Henner talked about that this is an interdisciplinary field. Yes, we are working hard with the legal teams from IPN and la Universidad Politécnica de Pachuca. Was very, very hard work. Now, oh my goodness, something fun. Okay, I need to talk. Last night, I forgot my password from my computer, and I don't know, in less than 1 hour, something happened. So sorry. Oh my God. Okay, sorry, but sorry for this. Is oh my goodness. Okay, okay. This is our team. I am this person. I don't know, and that's it. But we are working hard, trying to do together different kind of fields: medicine, legal team, students, physiotherapists, and we science computer research to become through this kind of space. This, and that's it. I don't know if you have questions about this work.
We have time for some questions.
Hi, good morning. Thank you for your presentation. I love it. I'm excited about that kind of infrastructure, about data and focus in medical. I have a question about the kind of access or collaboration. Are you, this kind of project is proposed only for institution or also for industry in order to improve this kind of solutions with AI?
First, it is necessary to include all kind and all sorts of people to have enough information and with enough quality. That's it. It's hard to say, oh, only private institution of health or only public. We try for 1 year. We are trying to gather people to our team, but was hard, really hard. The last 3 months, we found answer, but we need to motivate collaborative actions to build this kind of structures. Really, Mexican people need it. You use a lot of data sets, but which one are from Mexico? Yes, and we are trying to build this kind of structures. When we saw this I want to, if you want to go to the first one, please, to the first one slide. When we saw finally it's going to start in our teams, we will be so happy because finally we can use information, real information, that in models that can be used to improve the people, the health people. Yes, and that's it. Very relevant to have these teams. We are so proud. I hope that after this afternoon we have another team here, or maybe two. So we are trying to search people that believe in this kind of project. That's it. So yesterday I was talking with Danny, and we was so happy when they told me maybe you can see some approach to the classification without diagnostic. Oh my goodness, I was so happy because this reduced the pressure in our team. So we are so happy for the results. So I don't know. Another question.
Questions?
Thank you so much, Doctor.
You are the lady that I want to say thank you.
My question is actually not a big one. It's more like something not so serious about the about the one of the issues you raised about data. You mentioned data traceability.
Yeah.
To be able to trace a data to the particular source. So, but in one of your presentation, you mentioned that you're using, I think, about 3 blocks when you're talking about the blockchain. You're using about 3 blocks, one to rename the patient for the sake of privacy, like to hide, not to say, oh, the person that owns this record is Tommy, but to use another kind of nomenclature, a kind of naming, maybe to just say A1. I don't know if you understand what I'm trying to say. So my question would just be that with the blockchain and the and the other way of naming, I want to believe that for you who are the ones building this data ecosystem, you will still be able to trace back each record to probably at least the source to say, okay, this one we obtained it from Salvador Zubrian, or this one we got it from IMSS Tijuana, or this record we got it from IMS Pachuca. Mm-hmm. That's just what I'm trying to, I want to assume that is the situation.
Okay, let me talk more about the traceability here. Traceability is because we need to protect data without loss. Who is the owner? Yes. First, for the people that make donation to this platform. So in sometimes they want, I don't want that my data is there. So we need to recover this information and back to the owner. Yes. So another way could be that this information that you have, who is the owner, is from Mexico really, or is from another countries? This kind of answers are necessary in this platform, because we are talking about that Mexican people with a specific health conditions to analyze. Traceability is more than only legal condition, because this is another question. Do, your platform is covering all legal restriction in Mexico? You can show me how, and we need to show how the process of anonymization, protecting data we do. So traceability help us to do it. In fact, every action that we do over the data, we save in a blockchain. So this is our intention to use traceability. Or when a research use our data, who are using this data? What they are doing with this data? Where are they from? This kind of question must be to be answered. So traceability is more than only safe things. Maybe you can do some analysis or studies only with the blockchain. Blockchain is another way of analyze the information inside of the data ecosystems. I think that, I don't know if I.
My last question would just be, what is the state of the art of this work? Like, where are we at? Do you already have sufficient data to finalize or build this system and make it working? Or you are still in the process of collecting, gathering sufficient data? And is there a limit?
And
I'm sorry, is there a limit? Do you have a specific, okay, we just want 1 million records? Nada más.
Nada más. Okay. For the first questions, I told you that the 3 months, the last 3 months, we will happy when we have this INS start with us. So we have now 70 hospitals and maybe 10 years of information. So we need to process this. The question is, we need the capacity. I asked to the Dr. Montiel Rose, how much we have? 7 terabytes. Okay, and I go to there and I say, I don't. So we start to talk. Maybe we can have I don't know, fiesta party to gather more money to both more space. And so that's it. The new idea here is, I don't want your image. I only want to explore your space and training my models. And here, Mexico, are all AI models, and that's it. I don't want your image. You protect your data. I only want to train your models, not my models. Your models, your AI models, and working with like that only. So I don't know if answering your question. And that's it.
We have one question from YouTube. What computer languages are you using?
As I told you, we are using Go like backend now. We are using React. It's our first version. I don't know if you can help me to show our first approach. This is in process. We have two spaces. The first one is this electronic library, but the second one is a repository that the Dr. Montiel needs to give to CONACYT, but we hope that yeah, please don't put this one. Move the next one. The link, please. This use this one and this one, please. Dr. Montiel don't see this site, so we try to. So I hope this is the place. This is the place of the digital library. Here you can do physical donation. That means that if you come to Citeri, and I have several images printed image, you can give them, and finally you can cooperate with this structure, and you can use you can make donation of electronic image too. So this is the space, and this space is called or this way because we have two products. This is not the repository. This is the electronic library. So see it. And with this is maybe with Go as backend and red in HTML and another Python in some parts only, but not at all. Another question.
Thank you for your presentation. Give an applause to the presenter.
Now I invite you to the coffee break that we have prepared at the central patio located on the first floor. Remember that our next lecture will start at 11:20, so please be here on time. Thank you.
morning. Welcome to the next presentation from containers to the cloud scaling event-driven evolutionary algorithms by Mario Garcia from Instituto Tecnológico de Tijuana. Welcome.
Hi, good morning. How was the coffee break? I see that you are all very happy. So, well, here I'm going to present um, a brief experience about the work that we have been doing uh, a few years about the principal idea was scaling evolutionary algorithms. But in this presentation, we're not going to focus that much on the evolutionary algorithm part. We will be talking more about the experience, about using the technology, containers, and the cloud. And we are going to compare and give you my experiences about how to move uh, a common algorithm to these new technologies. So it's going to be more on the practical side. And I think also that this knowledge is applicable to all algorithms, to neural networks and other algorithms. So I hope you find this interesting. I'm doing I'm pressing the right. Oh, it's okay. I see many students and researchers. And sometimes when you're a student, your advisors tell you, okay, if you're going to do experimental computer science, well, you are going to propose an algorithm, then gather data, run experiments, validate the results. If you're a researcher, maybe write a paper or your thesis, and you're done. But you go to do it, and you find that gathering data is not that easy. Running the experiment is not that easy also, and validating the results. So everything is hard because you have to do a lot of work. And no, there's not such thing as done because you have to do it again. So this is a common problem. And we also consider the science part, but also distributed computing, SQL, parallel version control, a lot of things that goes into implementing our algorithms in some technology. And we also interested in, after we do our research, that is published, but also replicable. So there are, as we saw in the previous talk, some agencies that want to keep track of all the things that go into the development of our science. Not only the publication, but also the data, the workflows, the logs, slides, but also if it is code, maybe linked open data, the executable, the source code, and that we want this to be discoverable and reproducible. So we are going to focus on this work on the executable and reproducible part. I find this idea of executing code to be a task that involves installing a lot of software, installing the operating system, and doing a lot of work. One tool that I recommend is using something like Jupyter Notebook or Kaggle. I saw that someone mentioned. Here we have something that is very important. We can write like a paper, and then we can put the code along with the paper. And also something very important, we are doing this in a server. So this server can be very powerful, and we don't need to worry about that. We just put our code, our ideas, and maybe this can become a paper or something very important. And the other thing is that it's already almost ready to be published. We can put ideas and test things very easily. And we can scale this for instance, in Google Colab application, we can find that we can even use powerful computing, and this is very easy. So, but sometimes a notebook is not enough. Sometimes we are worried about problems that cannot be solved only in a single script, but maybe use distributed computing, other languages and tools not available in these applications, and we need maybe to do more research about the operating system or even the chips that we are talking about. And we need to measure the power consumption, some things that limit the use of this kind of technology. But our algorithms, as we also heard earlier, need a very powerful computers. So many of us turning to cloud computing like the answer. Okay, we are going to have something like this, but not in our department, in someone else's data center. And this is very successful in the enterprise because the enterprise needs to be scalable without any problem. So it needs to be elastic, and also it's used for mission critical applications. So if something goes wrong, we can have very fast another computer that takes over. So the cloud is really prepared for this kind of computing. But in my experience from experimental computing perspective, we don't need this scaling, and a lot of the things that the cloud computing offers us is not really needed. So I can say that sometimes you're paying for something that you are not really using. Okay, but the good thing of this is that we can specify a complete computer infrastructure for an experiment using code. For me, this is the most powerful thing about cloud computing, that you don't need to go to an interface and put all the things that you need. You can make a script that you can then share, and some other person can take this script, run it, and then they have the same, exactly the same infrastructure as you have and that you use for your experiments. And but another thing that is happening is that the way that systems are developed is also changing. It's moving to this kind of architecture when we have microservices, and these microservices are implemented as container, and they are normally run in the cloud, but they can run also in a hosted or a private data center or in our computers. So this is the way that is developing the systems in the enterprise. And I normally use this event architecture that I have found that is very easy to implement and is really powerful. And this is the idea, the main idea, I think, that I want to share in this talk. So for instance, we're going to have events. Events are packages of information, and this can be, for instance, an experiment that you want to run. If you are optimizing, for instance, a neural network, maybe this is the configuration of the neural network that you want to run, and you produce many experiments, and then you put it in a message queue, and this message queue is ready to accept many consumers of the same event. And this is a very easy way to parallelize the execution of your experiments, because this consumer can be a computer, a program written in a computer, or even for instance, in a browser with JavaScript. Everything that can process this kind of event can be a consumer, and this is very scalable because if you start to receiving many events, you can scale adding more and more and more consumers. So this is the basic idea of this event-driven architecture. And this is also asynchronous because there's no need to do coordination between the producer or the consumers, or they are very decoupled. Okay, and containers are also a powerful tool because it's like a virtual machine, but it's implemented using Linux. Normally, this Docker container technology, and there is no need to virtualize the computing. It runs very fast, and you can create containers and destroy them very, very fast. And there's also a cycle in the container. For instance, if I want to implement a service, for instance, I want to have a Redis memory database, I can make a container and then create an image. And then with this image, I can create many, many containers of the same image. So I can have repositories or registries where I can put the description of images. So this is very easy to share with other parties. And this is the way that you can specify how a container is going, what a container will contain. For instance, I can start from a container that has a Python, this version, and then inside this container, I can run this code, and then I can create an image with this specification, and then run several containers using, for instance, this other specification where several containers are described, and then I can launch, for instance, this kind of architecture with just these two files. So it's very easy to create this, and I can put this in a registry. I can give you the name of the registry, and you download and execute the same architecture in your computer locally or in the cloud. So we use a genetic algorithm as an example. I'm just going to talk about how we passed how we implemented the genetic algorithm this way. So we use something similar to a multi-population or Iceland model, where we have several isolated GAs running in a processor, and then after some time, several of the candidate solutions goes from one island to the other. And what we did was to put this in an event. We put the state of a population and then the parameters for the GA. So this is going to be a message or an event. And then we put this to a message queue. And then we have several workers, the containers that we saw before. And this, what they do is run a GA on this population with these parameters, a few generations, and after they finish, they put all this, the current state of the population with other information into another queue, and then all the populations that I put here in this queue are pulled from a mixer that takes some of the population and then mix them together, creates another message like this, and put it again to evolve. So this is basically each of a cycle over here runs the population several generations, and this way a very scalable implementation of a genetic algorithm is implemented. We tried this in other papers, giving solutions that is very competent. The algorithm, the results about in this, because we can change the parameters, and it gives good results, but it's not that the thing that we are talking here. I'm going to skip this part of the genetic algorithm, and I'm going to talk about implementing this. For instance, I ran this configuration in my local computer, for instance, with a population size. As you can see, the populations, because there are many populations, are small, and then did function evaluations, ran it. It ran great, but then I also implemented this in the Amazon container service. There are several options of this service. This one is the most practical because all all the provisioning of the instances are run by AWS, or there's another option where you can specify exactly the type of instance where you want to run your algorithm, and then you have to do all this in Amazon. You have to upload your image specification, then define the task definition. This is similar to Docker container. Then you run all your tasks. And the good thing is that you can keep logs about each process. Or if you choose to run this in a EC2 model, you specify what kind of computer are you using, and then when the container is created, it's run over there. Here's some images about how you can do this with an interface. Here are the prices of the GPUs, and I'm going to pass to the conclusions. I think it's here we can see, and the final conclusion is that it turns out to be very expensive to run this in AWS. If you have already resources assigned, for instance, in a grant, it's convenient, but it turns out that running an experiment in AWS 30 times costs about $500. And this I can run in my computer. It's actually a good computer, but so you can see the difference between the cost and the implementation. Finally, there's a special kind of container, excuse me, instances that are called on demand, and then others that are called spot. The on demand, the ones that I use are more expensive because you use it instantly. And the spot, you put like a requirement, and if a machine is free, you can use it then. So, but it's not ready already available. So that's my talk.
Thank you, Mario, for your presentation. It's time for questions.
Hello, thank you for the presentation. Yeah, I do have a question based on the event-driven architecture you presented. One of my question is, based on the principle that everything is asynchronous, how do you trace whenever there is an error? So yeah, basically, how do you trace that?
Okay, an advantage that I have here in a population event, in an evolutionary algorithm, is that if a message, for instance, is lost or something happens, I only record that there was an error, but actually the experiments continue evolving, and there's no problem if you lose, for instance, some of the messages. The genetic algorithm is capable of losing that information. So we did experiments about that, because before we did this same event-driven development using browsers. So you can enter our web page, and then you take a sample of the population and starts evolving better. In a browser, everyone can close, for instance, their window, and you lost all that message. Over there, we did something that we kept the population store also in the server, but we did experiments, and actually you have to do like 60% of the messages lost to lose something in the genetic algorithm. For this special kind of problem, there is no problem if you lose a population of one of the populations that you are working on. So we didn't actually care about that kind of problem.
Is there another question?
Very interesting work. Thank you for your presentation. I have a question about the benchmarking. For example, this proposal, have you seen other kind like terraforming configuration, like for high level, or other solutions that exist like machine learning flow with separating the containers? Are you considering this proposal to testing with this other kind of ways
to orchestrate the,
yeah, well,
okay, we also tested other containers orchestrated, for instance Kubernetes, but we find that this is created for the enterprise. Well, what you need is to be elastic, and if you see some demand, you put more computing power. So it's a lot of things that are not useful in our case, because we just want to run some task with normally as the same resources every experiment. So we found that it was not needed for this. That is not needed for experiments like the ones that we run. It's too much work and too much complexity that is not really needed. So I found, for instance, there's a orchestrator service that is called Docker Swarm that is very limited, but it's very easy to implement, for instance, in a lab, in a local lab. So that kind of solutions I will find, and I will stay away from over complex solutions like that one.
Thank you, Mario, for your presentation.
Thank you.
Welcome to the next presentation entitled Artificial Intelligence in Astrophysics, Analytical Enhancement by Carlos Guerrero from Universidad Autónoma de Nuevo León.
Carlos Alberto Guerrero Peña graduated with a bachelor's degree in physics from the Faculty of Sciences at UNAM. He completed his master and PhD studies in sciences with a specialization in astronomy and astrophysics at the Institute of Astronomy at UNAM. Following this, he undertook 4 postdoctoral stays at the National Observatory of Rio de Janeiro from the Ministry of Science, Technology, and Innovation in Brazil. In 2017, he became an associate researcher at the Institute of Astronomy at UNAM, where he also served as a resident astronomer at the National Astronomical Observatory. In 2023, Dr. Guerrero joined the Faculty of Physical Mathematical Sciences at Universidad Autónoma de Nuevo León as a full-time professor and researcher. His research focuses on high spatial resolution and high cadence observational studies applied to stellar astrophysics, multi-technique analysis of star formation and evolution in homogeneous samples of celestial bodies in the Milky Way, planetary sciences, astronomical instrumentation, and big data and machine learning techniques coupled to astrophysics. I hand over the word to Carlos Guerrero.
Thank you. Hello. Good morning. Good afternoon right now. So let's jump right in because I have many things I want to say. So I will start by giving you an overview of, this is my collaborators from here from CITERI. He's Dr. Juan Jose Tapia Armenta and our students, Luis Hector and Ana Victoria. And let me tell you that astronomy is going through a phase, through a phase changing. Right now we have this thing that is becoming very, very relevant called multi-messenger astronomy, where we are mixing we're not mixing, we are using every information that we can from the properties of the matter. For example, we have the complete spectrum of light from gamma rays to X-rays, ultraviolet light, infrared light, visible light. We have microwaves, radio waves. But right now, we are also including cosmic rays. We are including neutrinos physics and gravitational waves, right? So you can see that there's a tsunami of information that's arriving because of the advent of new technology, like wide field cameras that can observe a large region of the sky at the same time, and ever larger telescopes that are being built right now, and also space telescopes like the James Webb telescope that you might have heard. Then you can see that right now, astronomical data, it's amounting like petabytes of information, right? And you can see that with that advancement of these new technologies, well, the information will just keep growing, right? Just for you to have an idea, what we can achieve in a complete period of a mission, for example, a decade of previous generation of instruments, we can go obtain that information in a single night. So it's so much information that's coming in our way. Therefore, well, astronomy is becoming like a big data science. Well, we require the knowledge of big data, but it's not enough. Okay, we can say, okay, with the tools of big data, we can process our information, but we need more than that. We will see why. Why? Because we need to perform real-time analysis of our data. It's not enough to have processing tools. We need to analyze the information, right? So we need high efficient procedures to process our data. Then we can apply machine learning techniques. Scalability is not enough, like I said, right? We in the domain of data science, we can answer these questions. For example, how can we learn? How can we use a process of machine learning if our data is biased, right? We have been hearing across the seminar, okay, I don't have enough data, I have missing points, we can escalate our data, but this is not a trivial task, right? It's not, how can we do this without losing the information or including additional bias, right? How can we handle measurements in noisy measurements? Because specifically for astronomy, data it's affected by cosmic rays, for example. No, they hit the cameras. It's a wrong measurement, right? It could pass like a star, but it's not. How can we select the best features to be able to study our celestial objects? So all of these topics can be addressed using the tools of machine learning, right? So just for you to have an idea, this is the growing, a plot showing the growth of astronomical data that is being produced per night, okay? Right here in the 20s, we have the Sloan Digital Sky Survey. This mission was very successful. We still are using this data, and it was a mission that took 1 terabyte of data in the 20s, and it took 3.5 years to process this data, right? And now look at these telescopes that are producing 90 terabytes of data per night, right? The James Webb telescope, it's producing 65 gigabytes of data per half day, right? So it's not only a technology, a problem of processing the data, also of transmitting the data. No, well, this is another problem. So astronomical research is shifting. This is a paradigm shift, okay? Previously, we have like an idea, a hypothesis, and we propose an observing time. We went to the telescope, observe, process our data, and publish our results. Well, this process could take almost a year, right, to do that. Now we have these large surveys that are mapping the whole sky, producing many data with not a specific objective. So we go to the data, we download the data, and we can study the data. So it's a paradigm shift, okay? It's heavily data-driven right now, astronomy, the domain of astronomy. So let me show you an example of what we are doing right now. We have this picture of an open cluster of stars. You can see the colors of the stars, right? And you can see that they are red, they are blue, some of them are bright, some of them are dim. And if you only look at this picture, you cannot say anything about the stars unless you know a little physics, right? You can say that we know that red stars are colder than blue stars that are hotter, right? Because of some distribution that I will show you. It's called a spectrum. We plot the intensity as a function of wavelength, as a function of the color. And because of the physics of the stars, we can study the spectral distribution, right? So these plots are called spectra, and we separate them between classes, O, B, A, F, G, K, N stars, right? This is a separation of temperature. And you can see another number, 5, 0, 6. It's an interval between the temperatures, right? And you can see another letter here. It's a V. It's 5 in Roman number. This will tell us what kind of stars we have. So these plots, it's very relevant for me to talk about this. This is a seminar of quantum computing, right? And we're using tools of quantum mechanics to do something with them in the domain of machine learning. Well, for you to be able to use the tools of quantum mechanics, we have to understand this plot. It's called a black body radiation distribution, right? And this plot was the one that originated the whole revolution of quantum mechanics, right? Because physicists of the 20th century could not understand this plot because we didn't understand that the energy distribution of the electrons in the atom were quantized, right? Then Planck went and introduced the Planck constant, and after that, well, we have quantum mechanics. So these plots are an intrinsic property of the stars. The shape of the plot depends only on the superficial temperature of the stars. Okay, you can see this is color and this is intensity. And for a hotter star, the maximum of the intensity goes to the blue side of the spectrum. For redder stars, they are colder. The maximum is at redder wavelength. So that's why we have these stars. I have to speak about this. Then, how do we analyze this? We use filters in astronomical passband, like a filter, a color wavelength filter. So we are studying different parts of the spectrum, and we can compare different stars because you can see that they are very different. For example, this star in here will have like 1, and this star in here will have a 0. Right? They are called magnitudes. And we use them to create a spectral energy distribution of the stars. Right? So combining this color index, we can create this plot. It's called an HR diagram, a Hertzsprung-Russell diagram, which distributes the stars in this region, the specific region. It's a fantastic plot because it's a statistical and evolutionary plot to study a large groups of stars. No? This plot is the most precise plot that we have until now. No, it was called from a space mission called Gaia, and I have very small time. Well, most of the stars fall into this line. It's called the main sequence, like the sun, and we have here the region of giant stars, and this is white dwarf stars. So this mission can calculate the distance to the stars. I showed you the plot. We cannot know the properties of the stars if we don't know the distance, okay? Because, well, I will enter in detail. So we have a collaboration with Spain and Brazil called the J+. It's a telescope that it's in Spain, and it's studying the northern sky using 12 photometric filters. I show you one with 4. With 12, we have so much more information, right? We can study the complete spectrum. And it's covering a large portion of the northern sky. And up to now, the data release 3, the third data release, has 43 million of celestial objects. So you can imagine we cannot do this by hand like we do previously. Right? However, it does not provide any of the astrophysical parameters that we need to classify our objects. So here center Gaia and our methodology that we are developing. So just for you to see, the filters covers the whole spectrum, right? This is the telescope. So let's propose a procedure to try to classify our objects. So before we even start, we have to pre-process our data. Makes most of the students might know or are realizing that even before you can use a machine learning procedure, you have to pre-process your data, right? And you can take so much time doing that. So that happened here. We have our magnitudes from the 43 million of stars, and we created this plot box plots to look for outliers, to have the best quality data. We filter by magnitude. The fainter stars we have to take out because they have very many noise. No? And well, after removing these outliers, we took advantage of the properties of the Gaia mission. They are two completely different missions. J plus, it's observing halo stars. Later, I can tell you what it is. And Gaia, it's observing like the movement and the distance of the stars. So that's why it can produce these parameters: temperature, effective, superficial temperature, luminosity, radius, gravity, metallicity, distance, extinction. So we perform a match with Gaia and J plus and found that they overlap over more than 11 million of stars. No? So well, we thought that's great, because with this we can train a model to classify the objects in J plus that don't have this information, right? Well, it's not that easy, of course. We perform a correlation analysis to see what of the we have many parameters. We have 12 magnitudes. We have all the parameters of Gaia, and we see that they are strongly correlated. So we perform a PCA analysis to select just the best characteristics. We found that 9 principal components were enough to retrieve the more than 90% of the cumulative distribution of the features. So, okay, we say, okay, we reduce the complexity of the data, and now we can train our models with this information. So, but now, again, not all of the stars of Gaia had this information of temperature and luminosity. So before we could even develop our training model, we perform a linear regression using XGBoost to calculate the luminosity and the temperature of the objects in Gaia that didn't have it. And we see that, okay, our correlation coefficient is very high, so maybe we are doing something right, okay? We use random forest to the luminosity. And with this, we discovered that the most important characteristic of Gaia, for example, to calculate luminosity, it's the distance. It's like I told you, we cannot know the brightness of the stars if we don't know the distance of the object, right? So, well, this is going well. And then, why we did that? To have the most comprehensive vector of characteristics to be able to train a model just to classify our stars. So with this vector of characteristics, we train a bifurcated strategy. First, we try to, well, not try, we categorize our stars by luminosity. And after that, we use another model to calculate the luminosity class, right? In spectral type. Remember OVA that separate the stars in temperature, and the luminosity class separates in the, remember, the main sequence, like the sun and the giant stars, right? And, well, just, I think I will skip this because I don't have many time. Just the characteristics that were the most important are the right characteristics. For example, the color index, that tells us the temperature, it's what was the most relevant, so it's okay. Then, well, it's the same. We try many models. I invite you to read our chapter to see the details of the models. And this is our statistics. You can see, for example, here, no? The accuracy for main sequence star, the accuracy for luminosity class, it's dominated by main sequence stars. That is to be expected because of the majority of the stars in the universe are in the helium burning phase in the core, like the sun, okay? They are burning hydrogen into helium, so this result agrees with the physics of the problem, so we are confident that this is true. For example, in here, you cannot see O and B stars, and you can see that the accuracy for A stars is very low. Why? Because in the halo of the Milky Way, there's no early type stars, like young stars, okay? There's many details of astronomy that I can discuss with you if you have doubt, but it's because of the intrinsic nature of the J plus mission, okay? It's the hotter stars are distributed in the spiral arms of the Milky Way, so it is to be expected. But again, it agrees with the physics of the problem. So we went from this, that many objects that are not classified, to many objects that now we can say, okay, confidently say these are main sequence stars, these are giant stars, these are white dwarfs, and we also could separate them into the spectral types, right? So how can we include quantum computing when you see these bars, no? Because in the frontier cases, the stars starts to overlap because they are very similar. They are sorry, they will fall. They are thermodynamical systems and they are homologous. So where's the frontier to say what type of star? That's what we have this overlapping, and we think that maybe quantum computing could help us to at least select the best characteristic features, right? Well, there's so much work to do. If you are interested, please contact us. Sorry, I went too fast because it was so much information.
Thank you, Carlos, for your presentation. It's time for questions. Okay, I have one question.
Hi. Do you mention of the data are increment in another time? For this data, what is? Is an image? Is an what type?
Yeah. Okay. We can divide it into two types of data. Astronomical data, it's imaging, right? So first of all, we have images, and after we process the images, we have tables. No? They are not heavy and disk drive, but they are humongous. So you have many data. Yeah.
Thank you, Carlos, for your presentation.
Thank you.
Welcome to the next presentation, evaluating the performance of machine learning, deep learning, and large language models in automated binary document classification by Ricardo Santiago from Instituto Tecnológico de Tijuana.
Ricardo Rioda Santiago Sanchez graduated with a degree in computer systems engineering from the Tijuana Institute of Technology and has participated in the 2019 National Physics Olympiad. He is currently working in the data science area at ITJ Labs. He's passionate about mathematics, physics, and the area of machine learning. I give the floor to Ricardo Santiago.
Hello, everyone. Today, I'm going to present our work titled Benchmarking Machine Learning, Deep Learning, and Transformer Models for Document Classification. This is the new title. So the purpose, the goal of this benchmark is to know when to use deep learning transformers versus machine learning classifiers. Also know when to use text classifiers versus image classifiers. So depending on your computational resources. So for document classification, in our case, we can classify documents using computer vision to create image classifiers or natural language processing to create text classifiers. So knowing that, I want to know what is the best approach. So I will answer these questions in this work. So for that, we have developed two tasks. One of them is to classify curriculum vitae documents. The way the classification problem is established is classify if document is CV or not. For the other task is to identify if the document is a scientific paper or not. So we have two data sets for each task. We can see we have the text data set. This is used to create text classifiers. The image data set to create image classifiers. So we train text classifiers and image classifiers for each task. This is one task, and this is the other task. So we train traditional machine learning models, deep learning models, and also we use transformers. Finally, we evaluate all of the models. Okay, so for the data,
we have 4 datasets. As you can see here in the slide, we use the RBL-C DIP dataset. This dataset contains around 16 classes. It contains budgets, emails, also resumes, and many more classes. Also, we use the resume corpus dataset. This dataset contains around 20,000 resumes in plain text. Also, for the papers, we downloaded papers from Archive, and also we have a private dataset that contains around 10,000 resumes from ITJ. Okay. For the data extraction, we have defined a text extraction tool that only processes images, Word documents, and PDFs. So the way it works is that first we identify the file type. For example, for an image, we use, once we know that the document is an image, we use tesseract to extract the text. For Word documents, we use pandoc to extract the text. For PDFs, we use PDF to text to extract the text. And then we save the text into a TXT file. Okay, so for the state of art, there are several works before our work. So one of them is the evaluation of deep convolutional networks for document image classification and retrieval. This work uses convolutional neural networks for classifying documents using images. For 2021, there's a work that uses transformers. Also, this work is the comparative study of long document classification. This work uses deep learning and also uses images and text. For 2022, this work trains 12 machine learning models for text classification, and the layout LM version 3 uses pre-trained models for document classification, also using text and images. So our work combines all of the variations. So we train traditional machine learning models, also deep learning models, and transformers, and also we train text classifiers and image classifiers. So the big picture is that once we collect the data, we create the datasets. As we can see, we have 2 datasets for each task. And then we split the datasets into train, validation, and testing. Then we preprocess the datasets. In the case of the text datasets, we remove the stop words and many other steps. Then we train the models, the machine learning, deep learning, and transformers models, and we calculate the metrics. Okay, for the models used, we use these 10 models. For example, the first 2 are the machine learning models. These are these 4. The next 4 are the deep learning models, and the last 4, this one, are the transformers. So the first 2 are used to create text classifiers and also image classifiers. For the next are used for create image classifiers. The text CNN and the chart CNN are used for to create text classifiers. These 2 for image classification, and the XLNet and BERT for text classification. Okay, the summary of the datasets. As we can see, we have 4 datasets. The CV text, this corresponds to solve the curriculum vitae classification problem, but using text. For the next one is the CV image, is the dataset used to solve the curriculum vitae classification problem, but using images. For the next 2 are paper text for solving the other task for using text, the paper image to solve also the paper classification problem, but using, in this case, images. So we have these are the samples for training, validation, testing, and we have 2 classes. Okay. Then after training the models, we evaluate them, and these are the results. So these are the results of the classifiers trained in the CV text dataset. Okay, as we can see, for the first two models, the first two classifiers, the machine learning classifiers, we notice that the time inference is faster than the rest of the models. For the precisions of these two models, the precision, the recall, and the MWA score show us good results. In the case of the deep learning models, the TechCNN and CharCNN, we can see the time inference is not fast. It's not faster than these two. And we can see that the precision, recall, and MWA score, they are not good enough, and they are not better than the first two. So for the transformers, the XLNet and BERT, we have really good performance, but the inference time is slower. It's not that fast as the traditional machine learning models. So for the next classifiers, the classifiers trained in the paper text dataset, we have similar results. We can see that for the first two classifiers, we have a really good performance. Also for the transformers, you can see XLNet and BERT. But in the case of TechCNN and CharCNN, we can see as the previous slide, not a good performance. So from these experiments, we can conclude that the best solution for text classifiers are the traditional machine learning models. Okay, then for the CV image dataset, so in this case, we can see that the first two models are not good as the rest of the models, even though the time inference is faster. So in this case, we can see that the deep learning and the transformers models they have a better performance. So for the next classifiers, the classifiers trained in the paper image dataset, we have similar results. The first two models, they don't have a better performance than the rest of the models. In this case, we can conclude that in the case of using image classifiers to solve our problem, using traditional machine learning is not the best option. The best option is using deep learning or using transformers. So finally, we have done a random sampling test. In this case, using even more data. So in this case, we can see that for the text classifiers trained to solve the curriculum vitae problem, we can see that they are really good to generalize new data, just by exception of the CharCNN. So we can see that this classifier doesn't have a good performance as the rest of the models. This is because we have done some extra experiments that we didn't include in this work. We use even more data, and we saw that this model increases the performance. For the paper text classifiers, we have similar results as the previous slide. Also, for the same reasons, the CharCNN doesn't have the best performance. Now, for the CV image classifiers, we notice that they don't have a good performance to generalize new data. Also, for the next classifiers, we have the same results, and this is because in the case of using text for classification, the vocabulary doesn't change over time. I mean, it doesn't change too much over time. But in the case of using images, it depends of the style of the document and the format between documents, because sometimes some people uses different styles for the style of the CV, so that changes. So you need even more samples. So for the conclusion, these are the conclusions. For text classification task, traditional machine learning models can outperform deep learning due to faster inference times and sufficient accuracy, especially when large training datasets are not available. Also, text classifiers generalize well to new data, largely to the stability of the vocabulary in CVs, while image classifiers face challenges. In general, classifiers trained on text data outperform those trained on image data. Okay. So for future work, we create a hybrid. The future work is to create a hybrid approach that integrates both text and image inputs rather than handle them independently. Also apply the training process to other types of documents, not only classifying CVs or scientific papers, and also create an ensemble model by combining machine learning, deep learning, and or transformers. I didn't include another extra future work. That is, we can also add a quantum layer at the end of the model to see we have a better performance. So thank you.
Thank you, Ricardo, for your presentation. It's time for questions.
Hello. I have a question. It's about the what format of curriculum vitae do you use to make your test? So I know that there are many formats to curriculum vitae. Some ones have color, some ones is an image, another have fonts, the different fonts and something like that. Do you have a format, a specific format of a curriculum vitae that you pass your models or your results?
Okay, yes, no, there's not a specific format. So we have used data sets from ITJ. So those CVs from ITJ, they are like we consider like real CVs because people they want to be hired. So I have seen the documents, some of them, and they don't have similar. They are all different. So also we have collected data from the internet, and they also are different. There's not a standard for the CVs.
Okay, thank you.
Thank you very much for your presentation, Ricardo. My question is in regards to the tests. You mentioned that you did a random sampling test, I believe. Is there what's the difference between just testing on the regular tests?
Okay, yeah, we use for the training, the validation and testing. We didn't include all the CVs from the ITJ, so we saved some of them to test all the models after all the training.
Okay, so it would be just out of all the information that you had, just separate information.
Yes.
Okay, thank you for your answer.
Is there another question? No. Thanks, Ricardo, for your presentation. Finally, welcome to the last presentation, hybrid quantum genetic algorithm with a stronger entanglement recombination process for maximizing coverage area of a set of unmanned aerial vehicles in natural disaster locations by Luis Enrique Ballinas from Universidad Autónoma de Baja California, Tijuana.
Enrique Ballinas, electronics engineer from the Instituto Tecnológico de Tuxtla Gutiérrez, Chiapas, Mexico. Master of Science in Digital Systems from the Center for Research and Development of Digital Technology of the Instituto Politécnico Nacional, Tijuana, Baja California, Mexico. and Doctor of Science in Digital Systems from the Center for Research and Development of Digital Technology of the Instituto Politécnico Nacional, Tijuana, Baja California, Mexico. He is currently a professor at the Universidad Autónoma de Baja California and the Centro de Enseñanza Técnica y Superior. His areas of interests are evolutionary algorithms, quantum computing, quantum evolutionary algorithms, fuzzy systems. I give the word to Enrique Ballinas.
Okay, thank you for the presentation. And after begin, I would like to say thank you for being here. Today, I'm going to present a very interesting topic, called it hybrid quantum genetic algorithm with a strong entanglement recombination process for maximizing the coverage area of a set of unmanned aerial vehicles in natural disaster locations. This work is in collaboration with Dr. Oscar Montiel and Dr. Anabel Martinez Vargas. The outline of my presentation is as follows. I'm going to start with a brief introduction about my work and some related words. Then very interesting concepts, to understand my whole work. After that, in the methodology section, I'm going to present the structure of my hybrid quantum algorithm, then some experiments and results, and finally, conclusions and future work. The main objective of my proposed hybrid quantum genetic algorithm with a strong recombination process from now on, HQGA strong, is to maximize the coverage area of a set of unmanned aerial vehicles, UAVs, in natural disaster areas. Different classical methodologies have been proposed to solve this problem. And when I say classical methodologies, I refer to algorithms that performs on conventional computers. Most of these papers in the literature tackle the problem of locating UAVs in a disaster zone as a path planning problem. It means they design a route from an initial point to a final point, avoiding obstacles. The approach that addresses the problem similar to my work, I show you in the reference 8. The main difference between this paper and my work is that in reference 8, they use a classical methodology and I use a hybrid quantum genetic algorithm. Well, the first concept that I would like to introduce is quantum computing. The basic unit in quantum computing is the qubits, okay? The qubits has interesting properties. The first one is the superposition principles that is defined as a linear combination of two or more state vectors that creates a new state vector in the same Hilbert space. A Hilbert space is a multidimensional space where you can perform vector operations, okay? To describe the states of a qubit, we use the Dirac notation as shown in equation 1. We use this symbol called psi. And if you see equation 1, we have two variables, C0 and C1, that represent the amplitude values of the qubits. When we perform the measurements on a qubit, we force to the qubit to collapse in a most probably state. It means when we apply this operation. The other characteristic is quantum entanglement. This occurs when a quantum state cannot be decomposed into the tensor product of its individual states, as shown in equation 2 and equation 3. For the experiments, we use the following disaster zone model, as shown in figure 1. Sorry, this is a square, a confinement square of 1,000 meters by 1,000 meters. Here, the set M represents the positions of the UAVs in the disaster zone, and N represents the positions of the mobile users in the disaster zone. Okay, the equation 4 represents the fitness function of my algorithm, where C is the ratio of the mobile users covered by a set of UAVs. V is the number of mobile users covered by the set of UAVs, and N is the total number of mobile users in the disaster area. The equations 5 to 8 are the restrictions of my work. The equation D represents the minimum distance between the mobile user and the UAV. Equation 6 is the path loss and represents the attenuation that the signal suffers. Equation 7, is the signal interference radio that should be above 3 decibels for a successful transmission voice. And equation 8 ensures that only one mobile user connect with only one with only UAV. Okay, my algorithm is represented in this pseudocode. Okay, is in step one, we initialize a generation counter. Then in step two, we generate random positions for our mobile users N. Then in step three, we initialize our quantum population QT using the strongly entanglement quantum circuit and RJ quantum rotation gates. These quantum rotation gates set a superposition or qubits. Our quantum population is represented by equation 5. A quantum population is a collection of quantum chromosomes represented by this symbol, okay? A quantum population is a collection of qubits where each qubit has its own amplitude value. Here is represented by alpha and beta. Then in step 4, we create a while loop that will finish when the maximum number of generations is reached. Step 5, we perform the measurement operator on our quantum population QT using the equation 6. This equation is a projection operator where the numerator represents a projection on the state of the qubit that belongs to the subspace defined by P, and the denominator ensures that the state is normalized. In step 6, we map the classical population. It means a collection of bits with random UAVs coordinates, as we can see in figure 2. The upper part of the figure represents the classical population, where 0 means that the UAV is not in the disaster area. In step 7, we evaluate this population. Okay, in our fitness function, we use this algorithm. If you see this algorithm, we can see some of the restrictions that I mentioned before. For example, in step 8, we can see the minimum distance. In step 10, we can see the path loss. Step 12, the SIR. And finally, in step 24, the coverage radio. In step 8, we create a new quantum population using a strongly recombination process, as we can see in figure 3. The recombination process is represented, the strongly entanglement, is represented by a square dotted line and is made of CNOT gates. In step 9, we update the adaptive rotation angle. Okay, we use a fuzzy inference system to update this angle. For both input and output, we use 8 membership functions, and for the inputs, the universe of discourse is from 0 to 1 and represent the coverage radio, and for the output, the universe of discourse is from minus 4p to positive 4p, and it represents the adaptive rotation angle. Step 10, store the best solutions in a set of best solutions BT. And finally, in step 11, we increment the generation counter. Okay, for the experiment, we perform 3 sets of experiments. The first set is to evaluate the overall performance of the quantum algorithms against the genetic algorithm. In the second set, we involve a statistical test regarding accuracy, and in the third set of experiments present a statistical test concerning convergence time. Okay, the first set of experiments, if you see both tables, we can see in column M is the number of UAVs that we use in the disaster zone, 5, 10, and 20. And if we see the column algorithm, we can see GA32 and GA100. Both are genetic algorithms. Okay, the main difference is that is the size of the population, and HQGA FARA, I'm going to say it like that, and the HQGA Strong, both are quantum algorithms. Okay, the main difference is that HQGA FARA uses a Deutsch-Josa quantum circuit as a recombination process. Okay, in the mean column, we can see that both quantum algorithms obtain better results than the genetic algorithm. Also, in the STD column, standard deviation results, we can say that the results are better since the standard deviation is smaller than the standard deviation presented by the genetics algorithms. So, well, we can say that the quantum algorithms performs better in accuracy and robustness compared to the genetic algorithms. And the results are repeated in table 2. For the second set of experiments, when we perform the statistical test regarding accuracy, we use the Shapiro-Wilk test to evaluate if the results obtained by the algorithms have normal distribution or non-normal distribution. Here, since the 3 algorithms obtain a normal distribution, we perform the Welch test student. Okay, the hypotheses obtained for both algorithms in the Welch test student are false. It means there is a statistical significant difference between the quantum algorithms and the classical algorithms. And here, the difference is in favor of the quantum algorithms since they obtain better mean results in the aforementioned experiments. Actually, the results repeated in table 4. And if we see table 5 and table 6 is the same experiment, but with 10 UAVs, we can see that the results are the same. And for 20 UAVs, okay, in the best case and worst case scenario, sorry, I forgot to mention what is the difference between best case and worst case scenario. And when I say best case, it's because I'm using 5 transmission channels. And when I say worst case, is because I use just 1 transmission channel. Okay, now for the third set of experiments, the statistical test regarding convergence time. Here we employ the number of generations instead of the runtime for each algorithm. Here we can see that the Shapiro-Wilk test is false for the 3 algorithms, so they have non-parametric distribution. So I decided to use Wilcoxon-Signet-Grant test, where for the HQGA FARA we obtain a hypothesis H04. It means that there is a statistical difference between this algorithm and the genetic algorithm. And if we can see in the mean results, we can see that the HQGA FARA needs only 18 generations to reach the optimal. In contrast, the genetic algorithm needs 180. Okay, for table 10, we can see that both hypotheses are false. So there is a statistical difference, and the difference is in favor of both quantum algorithms compared to the genetic algorithm, the classical. And here the results for table 11 and table 12 with 10 UAVs are the same. Okay, and actually for the results with 20 UAVs, okay, best case, worst case scenarios, the results are the same that I mentioned before. Okay, well, as conclusions, I would like to say some contribution of my work. The first one is the integration of a strongly entanglement quantum circuit as a recombination operator. According to the experiments, we can see the superiority regarding convergence time with the HQGA FARA. Okay, the other one is the implementation of the HQGA strong for the aforementioned problem, maximizing the coverage area of a set of UAVs in a disaster location. Okay, based on the experiments, the HQGA strong demonstrate better accuracy compared to the GA, and in the worst case scenario, performs better than the HQGA FARA. As a future work, we are going to evaluate our quantum proposal in a more expensive geographical area. Also, we are going to implement our HQGA strong in a real quantum computer, since all the experiments here were developed in a simulator. And finally, we're going to modify our hybrid quantum algorithm in order to determine the optimal path. It means we are going to combine path planning and with our hybrid quantum genetic algorithm. And that's it. Thank you very much.
Thank you, Enrique. It's time for our questions. Is there?
Thank you very much, Dr. Ballinas, for your presentation. My question was, is there a significant difference when running the quantum genetic algorithm when compared to its classical counterpart? Is there more processing time? Is it significant?
Okay. That's a very good question. Yeah, here it's for matter of time. I don't. Okay. Yeah, I don't present that results, but if you see my paper, yeah, okay, you can see that there is the answer of your question, but actually, yeah, there is a significant difference between the HQGA strong and the HQGA FARA. I don't remember very well, but in most of the experiments, the HQGA strong performs better than the HQGA FARA. I think the difference is because if we see the complexity of the quantum circuit, the complexity of the HQGA strong, it means its quantum circuit is less complex than the circuit presented by the HQGA FARA. So for that reason, maybe the HQGA strong performs better in convergence time than its counterpart.
Okay, thank you very much.
Good presentation, thank you. I have a question about the platform. What platform used to program in quantum computing?
Okay, the hybrid quantum genetic algorithm was developed on Python using the Qiskit simulators. Okay, and actually the classical genetic algorithm also was in Python. All was in Python using the IBM simulator.
You have one proposed to move the work on the another platform, or you only work with IBM and Qiskit?
Well, I would like to have a contract with IBM, but no, I use IBM because it was my when I started in the quantum world, it was the first platform that it was free, so I decided to use it. But the idea is if I have the opportunity to move to another platform, for example, like Amazon, well, I think it's very expensive, but well, and okay, if there are another, I would like to try in another. But now I'm working with the IBM platform.
Thank you.
Thank you, Enrique, for your great presentations. I got questions regarding the Deutsch-Josa algorithm that you mentioned. What is the function on your work?
Okay, the Deutsch-Josa algorithm in the HQGA FARA act like a recombination process. For example, in the HQGA strong, I uses the strongly entanglement quantum circuit. Okay, and well, the idea here is it was to compare the performance between the three algorithms. Okay, so well, the HQGA FARA in my previous works demonstrate that performs better, but here I want to explore if another recombination process works better than the Deutsch-Josa.
Hola, Enrique.
Hello.
I like you expand more about the result obtained because you use the fuzzy operator instead the classical operator to rotate the gates.
Okay, yeah. Well, sorry. Okay, yeah. For the adaptive rotation angle in my previous work, I used to employ a mathematical equation, but here I decide, well, like the Dr. Montel says, a false inference system, because in my previous work I saw that when I use the mathematical equation, the change of the adaptive rotation angle, it was not so it was too long. I mean, here the less is the increment of the rotation angle, the better the results that I obtain. So when I used the mathematical model, the mathematical equation, it was difficult for me to to uh, mm, um, to adapt this mathematical equation to my proposal. So when I use the fuzzy inference system, I mean this kind of system is uh, is great when you are working with uncertain data. And well, I obtain better results using these kinds of system. I mean a fuzzy system, okay, that with the mathematical model. Yeah, for that's the reason that I decided to change it.
Is there another question? Thank you.
I hope this event has met your expectations. For the closing ceremony, I would like to ask our host, Dr. Oscar Montiel Ros, to come up and address us with a few words.
Thank you very much. Good afternoon, everyone, again. Okay, as we conclude this enriching today's seminar on artificial intelligence and quantum computing, I would like to take a moment to extend my sincere gratitude to all of you. Your active participation and enthusiasm have been key to making this event a resounding success. First and foremost, I want to express my heartfelt thanks to our distinguished speakers for their insightful presentations. Your expertise and commitment have truly transformed this seminar into a platform for sharing knowledge and igniting fresh ideas in the fields of artificial intelligence and quantum computing. I would also like to give special recognition to the support staff who worked tirelessly behind the scenes to ensure everything proceeded seamlessly. Your effort for managing technical logistics to facilitate sessions have been instrumental in the success of this seminar. Over the past 2 days, we have delved into some of the most cutting-edge topics at the intersection of artificial intelligence and quantum computing. The insights shared and discussions held have not only expanded our understanding, but have also illuminated new pathways for innovation and collaboration. I'm pleased to announce that we plan to hold this seminar again next year, and it would be an honor to have you join us one more, bringing your unique perspective and ideas to what I am confident will be another exceptional gathering of minds. Please stay tuned to our website and emails for updates on next year's dates and details. We hope to continue building on the valuable connections and conversation initiated here. Thank you once again for your dedication and for generously sharing your expertise with us. Wishing you safe travels, and I look forward to welcoming you again next year. And with that said, I officially declare this seminar closed. It has been an honor sharing this time with you. Have a wonderful evening, and I hope to see you soon. Thank you. Thank you, Fernando.
Before you go, we would like to invite you to a group photograph and the main entrance of the building. And we still have some food from the coffee break. So if you want to join us after the photograph, you are welcome. Have a great evening.